A gentle journey through the layers of space. From the surface of Earth to the edge of everything we can observe, this is a slow, calming exploration of cosmic scale. No sudden movements, no alarming revelations, just the quiet architecture of the universe, revealed one peaceful layer at a time. The cosmos operates on scales far beyond human comprehension, yet each level follows a pattern of nested structures, like Russian dolls made of starlight and void. This journey moves outward, always outward, through increasingly vast domains of space. Each boundary crossed reveals another realm, another scale, another way of understanding our position in the infinite. The pace remains steady and unhurried. There is no race to reach the end, only a measured progression through the cosmic address that defines our existence. From the familiar blue sphere beneath our feet to structures so large they strain the limits of measurement, this exploration offers perspective without anxiety, wonder without overwhelm. The universe contains multitudes, and each scale deserves its moment of quiet contemplation. As the journey unfolds, the structures grow larger, but the tone remains constant. Calm observation, gentle narration, the soothing rhythm of discovery without distress. This is not a journey of danger or drama, but one of peaceful revelation. The universe is vast, ancient, and profoundly indifferent to human concerns, and there is something deeply relaxing about that realization. We are small, but we are here, and we can trace the nested layers of cosmic organization that surround us. From satellites to superclusters, from the edge of atmosphere to the edge of observation, this is a map of everything, presented as a lullaby for the cosmically curious mind. The journey begins at the surface, where atmosphere meets ground and human civilization clusters in patterns of light and shadow. Earth rotates once every 24 hours, a rhythm so fundamental that it defines the basic structure of human experience. Above the surface, the atmosphere extends in layers, each with distinct characteristics and purposes. The troposphere contains weather and breathable air. The stratosphere holds the ozone layer. The mesosphere burns up meteors. The thermosphere glows with auroras. And beyond them all, the exosphere gradually fades into the vacuum of space. At approximately 35,786 kilometers above the equator, a special orbital altitude exists where satellites remain fixed above a single point on Earth's surface. This is the geostationary orbit, a ring of human-made objects maintaining constant positions relative to the rotating planet below. Communication satellites occupy this zone, beaming signals across continents, enabling the global network of information exchange that modern civilization depends upon. Weather satellites observe cloud patterns and storm systems from this vantage point. The orbit itself is crowded with active satellites, defunct satellites, and debris from decades of space operations. From this altitude, Earth appears as a complete sphere, blue and white and brown, rotating slowly beneath the fixed orbital ring. The view encompasses entire hemispheres at once. Weather systems span thousands of kilometers. The curvature of the planet is obvious and unmistakable. Day and night divide the sphere into illuminated and shadowed halves, with the terminator line sweeping steadily westward as Earth turns beneath the sun. The geostationary orbit represents the outer boundary of Earth's immediate technological sphere. Beyond this ring, satellites follow different paths, elliptical or polar orbits that carry them through different regions of near-Earth space. But this particular altitude, where orbital period matches planetary rotation, marks a significant threshold. It is the edge of the zone where human presence is continuous and purposeful. Above this orbit, space becomes progressively emptier, darker, and more dominated by natural forces rather than human activity. the quiet hum of satellites maintaining their positions, making tiny adjustments with thruster burns, communicating with ground stations far below. This is the first layer of the cosmic address, the technological shell humanity has wrapped around its home world. Between Earth and its moon stretches a vast emptiness, a region known as Cis-Lunar Space. The average distance spans 384,400 kilometers, though the moon's elliptical orbit causes this distance to vary by tens of thousands of kilometers throughout each month. This void contains almost nothing, a few spacecraft on transit trajectories, occasional meteors, the solar wind streaming past. The gravitational influence of both Earth and Moon creates complex dynamics in this region. The Lagrange points, positions where gravitational forces balance, offer stable locations for spacecraft and natural accumulations of dust. The L1 point lies between Earth and Moon, approximately 326,000 kilometers from Earth. The L2 point sits beyond the Moon, in its shadow. These mathematical positions in space mark locations where objects can maintain relatively stable positions with minimal energy expenditure. The Moon itself dominates the far end of this region, a gray sphere of ancient rock, its surface scarred by billions of years of meteor impacts. The near side, perpetually facing Earth due to tidal locking, displays the Dark Maria, vast plains of solidified lava from ancient volcanic activity. The far side, hidden from Earth's view, contains fewer Maria and more heavily cratered highlands. The lunar surface records the violent history of the inner solar system, each crater a frozen moment of impact preserved in airless silence. Cis-Lunar Space represents humanity's next frontier of expansion. The Apollo missions crossed this void in the late 20th century, carrying humans to the lunar surface and back. More recent missions have established the possibility of sustained presence beyond Earth orbit. The region offers resources, particularly water ice in permanently shadowed craters near the lunar poles, and potential staging areas for deeper space exploration. But mostly, Cis-Lunar Space contains emptiness. The distance is vast by human standards, yet trivial on cosmic scales. Light crosses from Earth to Moon in approximately 1.3 seconds. Radio communications experience noticeable but manageable delays. The view from mid-transit shows Earth shrinking behind and the Moon growing ahead, both spheres suspended in absolute blackness, illuminated by the distant sun. The silence is complete. No sound propagates through vacuum. The darkness is profound, broken only by the steady light of stars and the reflected sunlight from planetary bodies. This is the first taste of true deep space, the first region where Earth becomes a distant object rather than an encompassing environment. The psychological shift that occurs when Earth becomes something viewed rather than stood upon marks a fundamental transition in perspective. Cis-Lunar Space is where that transition begins, where the familiar blue sphere starts its recession into the cosmic distance. Moving outward from Earth's orbit, the inner solar system contains 3 other major bodies and vast expanses of near emptiness. Venus orbits closer to the Sun at an average distance of 108 million kilometers. Its thick atmosphere of carbon dioxide creates a runaway greenhouse effect, surface temperatures hot enough to melt lead, atmospheric pressure 90 times that of Earth at sea level. The planet rotates backwards relative to most solar system bodies, its day longer than its year, shrouded in sulfuric acid clouds that reflect sunlight brilliantly, making Venus the brightest planet in Earth's sky. Closer still to the Sun, Mercury follows an elliptical orbit ranging from 46 million to 70 million kilometers from the solar surface. This small, dense world experiences extreme temperature variations, baking at 430 degrees Celsius on the sunlit side, plunging to minus 180 degrees in shadow. Its surface resembles the Moon, heavily cratered with vast plains of ancient lava flows and strange escarpments where the planet's crust buckled as the interior cooled and contracted. The Sun itself dominates the inner system, a sphere of plasma 1.4 million kilometers in diameter, containing 99.86% of all mass in the solar system. Nuclear fusion in its core converts hydrogen to helium, releasing energy that takes hundreds of thousands of years to migrate from core to surface, then 8 minutes to cross space to Earth. The solar surface churns with convection cells, sunspots marking regions of intense magnetic activity, solar flares erupting with energies that dwarf all human technology combined. The space between these worlds contains the solar wind, a stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. This plasma carries the Sun's magnetic field into the solar system, creating the heliospheric current sheet, a warped surface extending to the outer reaches where solar influence fades. Dust particles orbit throughout the inner system, remnants of asteroid collisions and comet passages, creating the zodiacal light visible from Earth as a faint glow along the ecliptic after sunset or before sunrise. The inner solar system is defined by warmth and proximity to the Sun. Temperatures remain high enough that volatile compounds like water ice cannot persist on exposed surfaces. The terrestrial planets here formed from materials that could withstand the heat of the early solar nebula, metals and silicates rather than ices and gases. This is the warm zone, the region where rocky planets cluster, where the Sun's energy flux is strong enough to drive active weather systems and, on at least one world, to power the chemical processes of life. The boundaries of the inner system are not sharp but gradual, defined more by temperature and composition than by distance. As the journey continues outward, the Sun's warmth diminishes, its apparent size shrinks, and the nature of solar system objects begins to change from rock to ice, from terrestrial to something altogether different. Between the orbits of Mars and Jupiter, roughly 2 to 4 astronomical units from the Sun, millions of rocky bodies orbit in a broad belt. These are the asteroids, remnants from the solar system's formation 4.6 billion years ago, prevented from coalescing into a planet by Jupiter's massive gravitational influence. The asteroid belt contains incredible diversity despite its reputation for uniformity. The largest member, Ceres, spans 940 kilometers in diameter, massive enough for its own gravity to pull it into a spherical shape, classified as a dwarf planet. Vesta, the second largest, measures 525 kilometers across, its surface marked by an enormous impact crater near its south pole. Pallas and Hygeia round out the 4 largest members, but beyond these giants, the size distribution extends downward through millions of smaller bodies. Most asteroids are irregular chunks of rock and metal, tumbling through space on orbits that take 3 to 6 years to complete. Their compositions vary significantly. C-type asteroids, the most common, are carbonaceous, dark, and primitive, containing organic compounds and water-locked in mineral structures. S-type asteroids are stony, composed primarily of silicate minerals and metals. M-type asteroids are metallic, thought to be fragments of larger bodies that differentiated into core and mantle before being shattered by collisions. Despite containing millions of objects, the asteroid belt is mostly empty space. The total mass of all asteroids combined equals only about 4% of the Moon's mass. The average distance between asteroids measures in the millions of kilometers. Spacecraft can traverse the belt without significant risk of collision. The objects spread so thinly that encounters require deliberate navigation. The belt marks a compositional boundary in the solar system. Interior to this region, temperatures during formation were high enough to prevent water ice from condensing. Beyond this region, The frost line, water ice, became a major component of planetary building materials. This transition explains why the inner planets are small and rocky, while the outer planets are massive and rich in volatile compounds. The asteroids themselves tell stories of the early solar system's violence. Many show evidence of catastrophic impacts, families of asteroids sharing similar orbits and compositions, fragments from the destruction of larger parent bodies. The belt is a graveyard of failed planet formation, a museum of primordial materials, a boundary zone between the warm inner system and the cold outer reaches. Some asteroids follow eccentric orbits that carry them into the inner system, becoming near-Earth objects, potential threats to planetary surfaces, including Earth. Others remain stable in the belt for billions of years, barely disturbed since the solar system's youth. The Trojan asteroids occupy stable Lagrange points in Jupiter's orbit, leading and trailing the giant planet by 60 degrees. These populations, trapped in gravitational balance points, number in the thousands. The asteroid belt represents a transition zone, the border between two fundamentally different regions of the solar system. Beyond this realm of rock and metal, the giants wait, massive worlds of gas and ice, dominating the outer system with their gravitational influence and their retinues of moons. The Sun's influence extends far beyond the visible planets, creating a vast magnetic bubble in interstellar space. This is the Heliosphere, the region where the solar wind dominates over the interstellar medium. The solar wind, a continuous outflow of charged particles from the Sun's corona, streams outward at speeds averaging 400 to 700 kilometers per second. This plasma carries the Sun's magnetic field with it, creating a complex structure that fills the solar system and extends far beyond. The heliosphere is not spherical despite its name. The solar system's motion through the local interstellar medium, traveling at approximately 26 kilometers per second relative to nearby stars, creates a teardrop shape. The leading edge, facing the direction of motion, is compressed. The trailing edge extends into a long tail called the heliotail. The boundary, where solar wind pressure balances interstellar pressure, is called the heliopause, located approximately 120 astronomical units from the Sun in the nose direction, much farther in the tail. Before reaching the heliopause, the solar wind encounters the termination shock, where it slows from supersonic to subsonic speeds. This boundary, crossed by the Voyager spacecraft in the early 21st century, marks where the solar wind begins to feel the pressure of the interstellar medium. Beyond the termination shock lies the heliosheath, a turbulent region where solar wind and interstellar plasma mix and interact. The heliosphere protects the inner solar system from galactic cosmic rays, high-energy particles accelerated by supernovae and other violent events throughout the galaxy. The Sun's magnetic field, carried by the solar wind, deflects many of these particles, reducing radiation exposure for the planets within. Without this protective bubble, radiation levels in the inner solar system would be significantly higher, with implications for planetary atmospheres and the possibility of life. The structure of the heliosphere changes with the solar cycle. During solar maximum, when the Sun's magnetic activity peaks, the solar wind strengthens and the heliosphere expands. During solar minimum, the heliosphere contracts slightly and cosmic ray flux increases. These variations, measured by spacecraft throughout the solar system, reveal the dynamic nature of the Sun's influence. The heliosphere is invisible to human eyes, detectable only through its effects on charged particles and its interaction with interstellar matter. It represents the Sun's domain, the volume of space where our star's influence exceeds that of the galaxy beyond. Within this bubble, conditions are dominated by solar processes. Beyond it, interstellar space begins, a realm governed by different forces, different densities, different magnetic fields. The Voyager 1 spacecraft crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018, crossing at a different location and revealing that the boundary is not uniform but varies in position and structure. Both spacecraft continue to transmit data from beyond the heliosphere, measuring the properties of the local interstellar medium, confirming that the transition from solar-dominated to galaxy-dominated space is real and measurable. The heliosphere defines the Sun's neighborhood, the first layer of cosmic structure beyond the solar system proper. It is vast by human standards, encompassing all the planets and extending more than 100 times Earth's distance from the Sun. Yet on galactic scales, it is infinitesimal, a tiny bubble around an ordinary star, one of hundreds of billions in the galaxy. Far beyond the planets, beyond the heliopause, a vast spherical shell of icy bodies surrounds the solar system. This is the Oort Cloud, named for Dutch astronomer Jan Oort, who proposed its existence in 1950. The cloud has never been directly observed. Its presence is inferred from the orbits of long-period comets that occasionally plunge into the inner solar system from seemingly random directions. The Oort Cloud is thought to begin at approximately 2,000 astronomical units from the Sun and extend to perhaps 100,000 astronomical units, roughly halfway to the nearest star. This places its outer edge at nearly 2 light-years from the Sun. The cloud contains billions or perhaps trillions of icy objects, most smaller than a kilometer across, composed of frozen water, methane, ammonia, and other volatile compounds. These objects are remnants from the solar system's formation, planetesimals that formed in the region of the giant planets but were gravitationally scattered outward by close encounters with Jupiter and Saturn. The cloud is divided into 2 regions. The inner Oort Cloud, or Hills Cloud, is a disc-shaped region that may begin as far out as 2,000 astronomical units. The outer Oort Cloud is roughly spherical, surrounding the entire solar system uniformly. The total mass of the cloud is uncertain, but estimated at several Earth masses, distributed across an enormous volume. Objects in the Oort Cloud orbit the Sun extremely slowly. A typical orbit might take millions of years to complete. At these distances, the Sun appears merely as the brightest star in the sky, providing negligible heat. Temperatures hover just a few degrees above absolute zero. The objects exist in a deep freeze, their compositions essentially unchanged since the solar system's formation. Occasionally, gravitational perturbations disturb Oort Cloud objects. Passing stars, the gravitational tide from the galaxy itself, or encounters with giant molecular clouds can alter orbits, sending objects falling toward the inner solar system. These become long-period comets, taking hundreds or thousands of years to complete a single orbit, approaching the Sun from any direction rather than following the ecliptic plane like short-period comets from the Kuiper Belt. The Oort Cloud represents the outermost boundary of the Sun's gravitational dominance. Beyond this shell, the gravitational pull of other stars becomes comparable to the Sun's. The cloud marks the edge of the solar system in the truest sense, the limit of the Sun's ability to hold objects in orbit against the perturbations of the galaxy. The darkness here is profound. The Sun provides no warmth, only faint light. The stars shine with the same brightness they show from anywhere in the local neighborhood. The constellations unchanged by the relatively small distance from Earth. The void between objects is vast beyond comprehension, each icy body separated from its neighbors by billions of kilometers. The silence is absolute, the cold is extreme, the isolation is complete. This is the outer shell of the solar system, the final layer of the Sun's domain. Beyond the Oort Cloud lies true interstellar space, the vast emptiness between stars, where the sun's influence fades to insignificance and the galaxy's structure becomes apparent. The solar system currently moves through a region of slightly higher density in the interstellar medium known as the local interstellar cloud, or local fluff. This cloud is a wispy structure of gas and dust, part of the larger complex of interstellar material in the solar neighborhood. The density is still extraordinarily low by terrestrial standards, approximately 0.3 atoms per cubic centimeter, but this is higher than the average interstellar density in the galactic disk. The local interstellar cloud measures roughly 30 light-years across. The solar system entered this cloud between 44,000 and 150,000 years ago and will exit it within 10,000 to 20,000 years. The cloud's composition is primarily hydrogen and helium with traces of heavier elements. Its temperature ranges from 6,000 to 7,000 Kelvin, hot enough to ionize some of the hydrogen, creating a partially ionized plasma. The cloud exists within a larger structure called the local bubble, a cavity in the interstellar medium approximately 300 light-years across. The local interstellar cloud is one of several small clouds within this cavity, each moving through the bubble at different velocities. The solar system's motion carries it through these structures, the heliosphere compressing and expanding slightly as it encounters regions of varying density. The interaction between the heliosphere and the local interstellar cloud shapes the boundary of the sun's influence. The cloud's pressure compresses the heliosphere, determining the location of the heliopause. Changes in the cloud's density or the solar wind's strength cause the heliopause to move inward or outward over time. The local interstellar cloud is not uniform. It contains density variations, temperature fluctuations, and magnetic field structures. These inhomogeneities affect how cosmic rays penetrate the heliosphere and how the solar wind interacts with the interstellar medium. The cloud's magnetic field, though weak, influences the shape of the heliosphere and the paths of charged particles. Interstellar clouds like the local fluff are common throughout the galaxy. They form from the debris of stellar winds, supernova explosions, and the general turbulence of the interstellar medium. They are transient structures, lasting millions of years before dissipating or being compressed into denser formations. The solar system's passage through such clouds is a normal part of its orbit around the galactic center. The local interstellar cloud provides a gentle environment for the solar system. Its density is low enough not to significantly compress the heliosphere or increase cosmic ray flux to dangerous levels. Its temperature, though high by human standards, is relatively cool for interstellar plasma. The cloud represents the immediate interstellar neighborhood, the medium through which the Sun and its retinue of planets currently travel. This region of space, though nearly empty, is not truly void. It contains matter, energy, magnetic fields, and radiation. It is shaped by the history of stellar activity in the local region, by ancient supernovae that created the local bubble, by the ongoing winds from nearby stars, by the slow churning of galactic dynamics. The local interstellar cloud exists within a larger structure called the local bubble, a cavity in the interstellar medium approximately 300 light-years in diameter. This bubble is a region of significantly lower density than the surrounding galactic disk, containing only about 1/10 the normal density of interstellar matter. The bubble is thought to have been created by multiple supernova explosions between 10 and 20 million years ago. When massive stars explode, they release enormous amounts of energy, heating and compressing the surrounding interstellar medium. Multiple supernovae in close succession can create expanding shells of hot gas that merge, excavating large cavities in the galactic disk. The local bubble is one such cavity, its interior filled with hot, tenuous plasma at temperatures around 1 million Kelvin. The bubble's boundaries are not sharp but gradual transitions to denser, cooler material. The bubble is not perfectly spherical. It extends farther in some directions than others, shaped by the density structure of the surrounding interstellar medium and by subsequent stellar activity. The bubble connects to other nearby cavities, creating a network of low-density regions in the local galactic neighborhood. The solar system's position within the local bubble is not central, but offset, currently located in a region of slightly higher density, the local interstellar cloud. The bubble's existence affects the solar system in subtle ways. The lower density reduces the pressure on the heliosphere, allowing it to extend farther than it would in denser regions. The hot plasma in the bubble emits soft X-rays, contributing to the diffuse X-ray background observed by space telescopes. The bubble's structure influences the paths of cosmic rays and the distribution of interstellar dust. Within the local bubble, several small interstellar clouds drift, including the local interstellar cloud through which the solar system currently moves. These clouds are denser and cooler than the surrounding bubble plasma, remnants of material that resisted the supernova shocks or condensations that formed later from instabilities in the bubble's structure. The local bubble is part of the larger structure of the galactic disk. The disk is not a uniform distribution of matter, but a complex, frothy medium with cavities, shells, and filaments created by stellar activity. Star formation, stellar winds, and supernovae continuously reshape the interstellar medium, creating structure on scales from light-years to kiloparsecs. The bubble represents the solar system's immediate galactic neighborhood, the cavity within which the sun has traveled for millions of years. The solar system's orbit around the galactic center carries it through different regions of the disk over time, encountering varying densities, temperatures, and radiation environments. The current passage through the local bubble is a relatively benign phase, the low density and lack of nearby massive stars creating a quiet environment. Eventually, the solar system will exit the local bubble, entering denser regions of the galactic disk. This transition, occurring over millions of years, will change the pressure on the heliosphere, potentially affecting cosmic ray flux and space weather in the inner solar system. Such transitions have occurred many times during Earth's history and will continue throughout the solar system's future. The solar system resides in a minor spiral structure of the Milky Way galaxy called the Orion Arm, or Orion Spur. This feature is a partial spiral arm, a smaller structure connecting two major spiral arms, the Sagittarius Arm and the Perseus Arm. The Orion Arm measures approximately 3,500 light-years in length and roughly 1,000 light-years in width. The structure contains a higher density of stars, gas, and dust than the interarm regions, though it is less prominent than the major spiral arms. The arm includes many familiar stellar associations and nebulae. The Orion Nebula, a stellar nursery where new stars are forming, lies within this structure. The Pleiades, a young open cluster of hot blue stars, is another prominent member. The Cygnus X region, an area of intense star formation, also resides in the Orion Arm. These features make the arm visible from Earth as a band of stars and nebulae stretching across the night sky. The solar system's position within the Orion Arm is not central, but roughly halfway between the inner and outer edges. The Sun orbits the galactic center at approximately 220 kilometers per second, taking roughly 225 to 250 million years to complete one orbit. This galactic year places the solar system in a relatively stable orbit, neither spiraling inward nor being flung outward. The Orion Arm is a region of moderate stellar density. The average distance between stars is roughly 5 light-years, similar to the distance to the nearest star system, Alpha Centauri, which lies 4.37 light-years from the Sun. This spacing means that stars are gravitationally isolated from each other, their influence on neighboring systems minimal except over very long timescales. The arm structure influences star formation in the region. The slightly higher density of gas and dust provides material for new stars to form, though the rate is not as intense as in the major spiral arms. The presence of young, massive stars in the Orion Arm indicates ongoing star formation, these luminous objects having lifetimes of only millions of years. The solar system's location in a minor arm rather than a major arm may have significance for the development of life on Earth. Major spiral arms contain more massive stars, which explode as supernovae more frequently. The increased radiation from these events could be hazardous to planetary biospheres. The Orion Arm's intermediate position provides a balance, enough stellar activity to enrich the interstellar medium with heavy elements, but not so much as to create a hostile radiation environment. The arm is not a fixed structure, but a density wave, a pattern that rotates through the galactic disk at a different rate than the stars themselves. Stars move in and out of spiral arms over time, spending portions of their orbits in the denser arm regions and portions in the less dense interarm regions. The solar system's current residence in the Orion Arm is temporary on galactic timescales, though it will remain in this structure for tens of millions of years. The Orion Arm represents the solar system's neighborhood in the galaxy, the local structure within which the Sun and its planets orbit. Beyond this arm lies the broader structure of the Milky Way, the spiral pattern of the galactic disk, and the massive concentration of stars in the galactic center. Orbiting through the Milky Way's halo, intersecting the galactic disk near the solar system's position, stretches a stream of stars known as the Sagittarius stream. This structure is the remnant of a dwarf galaxy, the Sagittarius dwarf elliptical galaxy, currently being torn apart by the Milky Way's gravitational forces. The stream wraps around the Milky Way multiple times, its stars spread along an orbit that takes them through the galactic disk and out into the halo. The Sagittarius dwarf elliptical galaxy was discovered in 1994, hidden behind the dense star fields of the galactic center. Despite being one of the closest satellite galaxies to the Milky Way, its discovery came late because its stars are difficult to distinguish from foreground Milky Way stars. The dwarf galaxy contains several million stars, a tiny fraction of the Milky Way's population, but its proximity makes it a significant feature in the local galactic environment. The tidal forces from the Milky Way's gravity are gradually destroying the Sagittarius dwarf. As the dwarf galaxy orbits the Milky Way, the differential gravitational pull across its structure stretches it along its orbit, pulling stars away from the main body and creating the Sagittarius stream. This process, called tidal stripping, is common in galaxy interactions, the larger galaxy's gravity inexorably dismantling smaller companions. The stream contains stars at various distances from the galactic center, some passing relatively close to the solar system. The stream's stars have distinct chemical compositions and kinematic properties that distinguish them from native Milky Way stars. Studies of these stars provide insights into the history of the dwarf galaxy and the process of galactic cannibalism. The Sagittarius dwarf has orbited the Milky Way for billions of years, completing multiple passages through the galactic disk. Each passage strips away more stars, gradually dispersing the dwarf galaxy's population throughout the Milky Way's halo. Eventually, the dwarf galaxy will be completely assimilated, its stars becoming indistinguishable members of the Milky Way's halo population. The interaction between the Sagittarius dwarf and the Milky Way may have influenced the structure of both galaxies. Some researchers suggest that passages of the dwarf galaxy through the Milky Way's disk could have triggered star formation or influenced the spiral structure. The gravitational effects of such interactions ripple through the galactic disk, creating density waves and perturbations that persist long after the dwarf galaxy has passed. The Sagittarius stream represents a snapshot of galactic evolution in progress. The process of a large galaxy consuming smaller companions is a fundamental aspect of galaxy growth and evolution. The Milky Way has assimilated many dwarf galaxies throughout its history, each contributing stars and gas to the growing galactic system. The Sagittarius dwarf is simply the most recent and closest example of this ongoing process. The stream's presence near the solar system means that some of the stars visible in Earth's night sky may be members of the Sagittarius stream rather than native Milky Way stars. These immigrant stars, torn from their home galaxy and now orbiting within the Milky Way's gravitational well, represent the dynamic nature of galactic structure and the violent processes that shape galaxy evolution. At the center of the Milky Way galaxy, approximately 26,000 light-years from the solar system, lies a region of extraordinary density and activity. The galactic core contains a supermassive black hole known as Sagittarius A star, with a mass approximately 4 million times that of the Sun. This object, though massive, occupies a relatively small volume, its event horizon only about 17 times the Sun's diameter. Sagittarius A star was confirmed through decades of observations tracking the orbits of stars near the galactic center. These stars, moving at thousands of kilometers per second, orbit an invisible object with immense gravitational influence. The closest approaches of these stars to the black hole provided precise measurements of its mass and location. The discovery earned the 2020 Nobel Prize in Physics. The black hole itself is surrounded by an accretion disk of hot gas spiraling inward. As material falls toward the event horizon, it heats to millions of degrees, emitting X-rays and radio waves. The black hole is not currently feeding voraciously, making it relatively quiet compared to the active galactic nuclei seen in some other galaxies. The galactic center region contains an extraordinarily high density of stars. Within the central parsec, millions of stars orbit in a complex dance around the central black hole. The stellar density is so high that close encounters and collisions between stars occur much more frequently than in the galactic disk. This crowded environment creates extreme conditions with intense radiation fields and complex gravitational interactions. The region also contains massive young stars, surprising given the harsh environment. These stars, some with masses over 100 times the Sun's mass, formed relatively recently in cosmic terms. Their presence suggests ongoing star formation even in the extreme conditions near the galactic center, though the mechanisms that allow gas clouds to collapse into stars in such an environment remain subjects of active research. Surrounding the immediate galactic center, the nuclear bulge contains billions of older stars in a roughly spherical distribution. This bulge extends several thousand light-years from the center and contains a significant fraction of the galaxy's total stellar mass. The stars in the bulge follow complex orbits, their motions shaped by the collective gravity of the entire bulge population. The galactic center emits radiation across the electromagnetic spectrum. Radio observations reveal complex structures of ionized gas. Infrared observations penetrate the dust that obscures visible light, revealing the dense stellar populations. X-ray observations show hot gas and the activity around the central black hole. Gamma-ray observations have detected a mysterious excess of emission, possibly from dark matter interactions or from a population of millisecond pulsars. The core of the Milky Way represents the gravitational anchor of the entire galaxy. The black hole's mass, though enormous, is only a tiny fraction of the galaxy's total mass, but its gravitational influence organizes the motions of stars and gas throughout the central regions. The bulge's collective gravity helps maintain the spiral structure of the galactic disk and influences the orbits of stars like the Sun in the outer regions. From the solar system's position in the Orion Arm, the galactic center appears as a bright band of stars in the constellation Sagittarius. Dust in the galactic plane obscures the view in visible light, but the sheer number of stars creates a noticeable brightening of the Milky Way in that direction. The core, though distant, dominates the galaxy's structure and evolution. Surrounding the Milky Way's disk and bulge, extending far beyond the visible spiral structure, lies the Galactic Halo. This roughly spherical region contains old stars, globular clusters, and vast amounts of dark matter. The halo is not sharply bounded, but gradually fades with increasing distance from the galactic center, its outer edge difficult to define precisely. The stellar halo contains individual stars and globular clusters, dense spherical collections of hundreds of thousands to millions of stars. These globular clusters are among the oldest objects in the galaxy, their stars having formed over 12 billion years ago, within a billion years of the Big Bang. The clusters orbit through the halo on paths that carry them through the galactic disk and out to distances of hundreds of thousands of light years. The stars in the halo have different chemical compositions than disk stars. They contain lower abundances of elements heavier than hydrogen and helium, reflecting their formation in the early universe before generations of stellar nucleosynthesis had enriched the interstellar medium with heavy elements. These population 2 stars, as they are classified, provide insights into the conditions of the early galaxy and the universe. The halo also contains streams of stars, remnants of dwarf galaxies, and globular clusters that have been tidally disrupted by the Milky Way's gravity. These streams trace out the orbits of their progenitor objects, wrapping around the galaxy in complex patterns. The Sagittarius stream is one example, but many other streams have been discovered through careful surveys of stellar positions and velocities. The dark matter halo extends even farther than the stellar halo, possibly reaching several 100,000 light-years from the galactic center. Dark matter, which interacts only through gravity and possibly through weak nuclear forces, makes up approximately 85% of the matter in the universe. The Milky Way's dark matter halo contains far more mass than all the visible stars and gas combined. The dark matter halo's gravitational influence shapes the galaxy's structure and dynamics. The rotation curve of the Milky Way, the relationship between orbital velocity and distance from the center, remains flat far beyond the visible disk, indicating the presence of substantial unseen mass. This dark matter provides the gravitational scaffolding that holds the galaxy together and influences the motions of all its components. The halo is not uniform, but contains substructure, density variations, and possibly streams of dark matter from disrupted dark matter subhalos. These features, predicted by simulations of galaxy formation, are difficult to detect directly, but may be revealed through their gravitational effects on visible matter or through potential dark matter particle interactions. The temperature of the halo's gas component is extremely high, millions of degrees Kelvin, hot enough to emit X-rays. This hot gas, called the circumgalactic medium, contains a significant reservoir of baryonic matter, possibly as much as the mass of all the stars in the galaxy. The gas is thought to be heated by supernova-driven winds from the galactic disk and by the accretion of gas from the intergalactic medium. The galactic halo represents the outer boundary of the Milky Way as a distinct structure. Beyond the halo lies the realm of satellite galaxies and the beginning of intergalactic space, where the Milky Way's gravitational influence competes with that of other members of the local group. The Milky Way does not exist in isolation, but is orbited by dozens of smaller satellite galaxies. These companions range from relatively large systems containing billions of stars to ultra-faint dwarfs with only thousands of stars. The satellites orbit within the Milky Way's dark matter halo, bound by gravity to the larger galaxy, gradually being consumed through tidal interactions. The two largest satellites are the Large Magellanic Cloud and the Small Magellanic Cloud, visible to the naked eye from the southern hemisphere as diffuse patches of light. The Large Magellanic Cloud contains approximately 30 billion stars and lies about 160,000 light-years from the Milky Way. The Small Magellanic Cloud, with roughly 3 billion stars, orbits at approximately 200,000 light-years. Both clouds show signs of tidal distortion from their interaction with the Milky Way, with streams of gas connecting them to each other and to the Milky Way. Other significant satellites include the Sagittarius dwarf elliptical galaxy, currently passing through the Milky Way's disk and being torn apart, and several classical dwarf spheroidal galaxies discovered in the 20th century. These include Fornax, Sculptor, Carina, and Draco, each containing millions of stars and orbiting at distances of hundreds of thousands of light-years. In recent decades, surveys have discovered numerous ultra-faint dwarf galaxies, systems so dim that they contain only thousands to tens of thousands of stars. These objects are dominated by dark matter, their visible stars representing only a tiny fraction of their total mass. The ultra-faint dwarfs are thought to be the surviving remnants of the building blocks that merged to form larger galaxies like the Milky Way in the early universe. The satellite galaxies provide natural laboratories for studying dark matter, star formation in extreme environments, and galaxy evolution. Their proximity allows detailed observations impossible for more distant systems. The chemical compositions of their stars reveal the history of star formation and enrichment in low-mass systems. Their orbits and internal dynamics constrain models of the Milky Way's mass distribution and dark matter halo structure. The relationship between the Milky Way and its satellites is not static. The satellites orbit the Milky Way on timescales of hundreds of millions to billions of years. During each orbit, tidal forces from the Milky Way strip stars and gas from the satellites, gradually dismantling them. The Magellanic Clouds are losing gas to the Milky Way, creating the Magellanic Stream, a ribbon of neutral hydrogen wrapping around the galaxy. The Sagittarius dwarf is in an advanced stage of disruption. Its stars spread in streams around the Milky Way. The satellite galaxies also influence the Milky Way. Their gravitational perturbations may trigger star formation in the galactic disk or influence the spiral structure. The accretion of satellite galaxies contributes to the Milky Way's growth, adding stars and gas to the halo and disk. This process of hierarchical assembly, small galaxies merging to form larger ones, is a fundamental aspect of galaxy evolution throughout the universe. The satellite system of the Milky Way is part of the larger local group of galaxies, a collection of gravitationally bound systems dominated by the Milky Way and the Andromeda Galaxy. The satellites orbit within this structure, their motions influenced by both the Milky Way's gravity and the collective gravity of the local group. Between the galaxies of the local group stretches vast emptiness, the Intergalactic Void. This space is not completely empty, but contains extremely diffuse gas, the intergalactic medium, at densities far below even the sparse interstellar medium. The average density in intergalactic space is approximately 1 atom per cubic meter, compared to millions of atoms per cubic meter in the interstellar medium of the galactic disk. The intergalactic medium in the local group is thought to be partially ionized, heated to temperatures of hundreds of thousands to millions of degrees by the ultraviolet radiation from stars and by shocks from galactic winds. This hot gas is difficult to observe directly, but has been detected through its absorption of light from background quasars and through faint X-ray emission. The void between galaxies is where the influence of individual galaxies fades and the large-scale structure of the universe becomes apparent. Galaxies are not randomly distributed, but follow patterns, clustering into groups and clusters, with vast voids between these structures. The local group occupies a relatively small volume in this cosmic web, a modest collection of galaxies on the outskirts of larger structures. The distance between the Milky Way and the Andromeda Galaxy, the two dominant members of the local group, is approximately 2.5 million light-years. This gap contains several smaller galaxies, including Triangulum, the third largest local group member, but mostly it contains the tenuous intergalactic medium. Light from Andromeda takes 2.5 million years to reach the Milky Way, meaning observations show Andromeda as it was in the distant past. The intergalactic void is not static. The galaxies of the local group are moving under their mutual gravitational attraction. The Milky Way and Andromeda are approaching each other at approximately 110 kilometers per second and will collide in approximately 4.5 billion years. This future merger will transform both galaxies, creating a single elliptical galaxy from the collision and merger of the two spirals. The void also contains dark matter, the invisible mass that dominates the gravitational dynamics of the universe. The local group's dark matter halo extends throughout the volume, providing the gravitational framework that binds the member galaxies together. The distribution of dark matter determines the motions of galaxies and influences the evolution of the group over cosmic time. Intergalactic space is filled with electromagnetic radiation, the cosmic background light produced by all the stars and galaxies throughout cosmic history. This includes the cosmic microwave background, the red-shifted thermal radiation from the Big Bang, and the accumulated light from all stellar sources. The void is also permeated by cosmic rays, high-energy particles accelerated by supernovae and other violent events, traveling through intergalactic space at near light speed. The intergalactic void represents the transition from galactic to cosmological scales. Within galaxies, stellar and galactic dynamics dominate. In the void, the expansion of the universe and the large-scale distribution of matter become the primary factors shaping structure and evolution. The void is where the individual characteristics of galaxies fade and the universal properties of spacetime and cosmic expansion take precedence. The Milky Way and its immediate neighbors form a gravitationally bound structure called the local group, containing more than 80 galaxies spread across approximately 10 million light-years. The group is dominated by two large spiral galaxies, the Milky Way and Andromeda, with all other members being significantly smaller dwarf galaxies and irregular systems. Andromeda, also known as M31, is the largest galaxy in the local group, containing approximately 1 trillion stars, roughly double the Milky Way's population. Andromeda is a spiral galaxy similar in structure to the Milky Way, with a disk, bulge, and halo. It has its own system of satellite galaxies, including M32 and M110, both visible in telescopes as companions to the larger galaxy. The Triangulum Galaxy, or M33, is the third largest local group member, a spiral galaxy containing approximately 40 billion stars. Triangulum lies approximately 3 million light-years from the Milky Way and may be a satellite of Andromeda, though its orbital relationship is uncertain. The galaxy is notable for its active star formation and the presence of numerous emission nebulae. The remaining local group members are dwarf galaxies of various types. Dwarf irregulars, like the Magellanic Clouds, contain gas and ongoing star formation. Dwarf spheroidals, like Fornax and Sculptor, are gas-poor systems dominated by old stars. Ultra-faint dwarfs represent the smallest and least luminous galaxies known, barely distinguishable from globular clusters except for their dark matter content. The local group, occupies a region of space approximately 10 million light-years across, though the boundaries are not sharply defined. The group's total mass is dominated by dark matter, estimated at approximately 2 trillion solar masses. The visible matter in stars and gas represents only a small fraction of this total, with the rest being the invisible dark matter that provides the gravitational glue holding the group together. The dynamics of the local group are dominated by the Milky Way and Andromeda. The two large galaxies are approaching each other and will eventually merge, an event that will reshape the structure of the group. The smaller galaxies orbit within the group's gravitational potential, some bound to the Milky Way, some to Andromeda, and some potentially orbiting independently. The local group is isolated from other galaxy groups by several million light-years of relatively empty space. The nearest significant galaxy group is the M81 group, approximately 12 million light-years away. This isolation makes the local group a relatively simple system for study, without the complications of interactions with other massive galaxy groups. The group provides a laboratory for studying galaxy evolution, dark matter, and the formation of structure in the universe. The proximity of local group galaxies allows detailed observations of individual stars, star clusters, and interstellar medium components. The variety of galaxy types within the group, from large spirals to ultra-faint dwarfs, provides insights into the processes that shape galaxies across a wide range of masses and environments. The local group is part of the larger Virgo Supercluster, a vast collection of galaxy groups and clusters spanning over 100 million light-years. The local group occupies a position on the outskirts of this supercluster in a region of relatively low galaxy density. The local group is not an isolated structure, but part of a much larger assembly of galaxies known as the Virgo Supercluster. This supercluster contains approximately 100 galaxy groups and clusters with a total mass of approximately 10 to the 15th solar masses. The structure spans approximately 110 million light-years and contains tens of thousands of galaxies. At the heart of the Virgo supercluster lies the Virgo cluster, a massive concentration of galaxies approximately 54 million light-years from the local group. The Virgo cluster contains approximately 1,500 galaxies, including several giant elliptical galaxies like M87. Which harbors a supermassive black hole with a mass of 6.5 billion solar masses. The cluster's gravitational influence affects the motions of galaxies throughout the supercluster. The Virgo supercluster has a flattened, disc-like shape, with the Virgo cluster near the center and various galaxy groups, including the local group, distributed throughout the structure. The local group occupies a position on the outskirts of the supercluster in a region of relatively low galaxy density, sometimes called the local sheet. The supercluster is not a gravitationally bound structure in the same sense as galaxy groups or clusters. The expansion of the universe overcomes the gravitational attraction between the supercluster's components, causing the structure to gradually disperse over cosmic time. However, the supercluster represents a significant overdensity in the distribution of matter, a feature that formed from small density fluctuations in the early universe. The galaxies within the Virgo supercluster exhibit bulk motion toward the Virgo cluster, a flow pattern called the Virgo-centric flow. This motion reflects the gravitational influence of the cluster's mass, pulling nearby galaxies inward. However, more recent observations have revealed that this flow is part of a larger pattern, with the entire Virgo supercluster moving toward an even more massive structure. The Virgo supercluster contains a variety of galaxy types and environments. The dense cores of clusters contain primarily elliptical and lenticular galaxies, systems that have exhausted their gas supplies or had them stripped away by interactions with the hot intracluster medium. The outskirts and lower density regions contain more spiral galaxies, systems that retain gas and ongoing star formation. The supercluster's structure reflects the history of cosmic evolution. The distribution of galaxies traces the underlying distribution of dark matter, which formed the gravitational framework for structure formation. The filaments, sheets, and voids visible in the supercluster structure are characteristic of the cosmic web, the large-scale pattern of matter distribution throughout the universe. Observations of the Virgo Supercluster have been crucial for understanding galaxy evolution and cosmology. The variety of environments within the supercluster allows studies of how galaxy properties depend on local density and interactions. The supercluster's structure and dynamics constrain models of structure formation and the properties of dark matter and dark energy. The Virgo Supercluster was long considered the largest structure containing the local group, but more recent mapping of galaxy motions has revealed that it is itself part of an even larger structure, the Laniakea Supercluster, a vast assembly of galaxies spanning 500 million light-years. In 2014, astronomers announced the discovery of Laniakea, a vast supercluster of galaxies that includes the Virgo Supercluster and several other major structures. The name means immeasurable heaven in Hawaiian, reflecting the structure's enormous scale. Laniakea spans approximately 520 million light-years and contains approximately 100,000 galaxies, with a total mass of approximately 10 to the 17th solar masses. Laniakea was identified through mapping the peculiar velocities of galaxies, their motions relative to the smooth expansion of the universe. These peculiar velocities reveal the gravitational influence of mass concentrations, allowing astronomers to trace the flow patterns of galaxies through space. The boundaries of Laniakea are defined by the watersheds in these velocity flows, regions where the gravitational pull changes direction. The structure of Laniakea resembles a vast cosmic basin, with galaxies flowing along filaments toward regions of higher density. The Virgo Supercluster occupies a position on the outskirts of Laniakea, with the entire supercluster participating in a bulk flow toward the center of the larger structure. This flow has been measured at approximately 630 kilometers per second. At the heart of Laniakea lies the Great Attractor, a massive concentration of galaxies in the direction of the constellations Hydra and Centaurus. The Great Attractor's gravitational influence dominates the dynamics of Laniakea, pulling galaxies throughout the supercluster toward it. However, the Great Attractor itself is not the final destination of this flow, as it too is moving toward an even larger mass concentration called the Shapley Supercluster. Laniakea is not a gravitationally bound structure. Like the Virgo Supercluster, the expansion of the universe overcomes the gravitational attraction between Laniakea's components. The structure will gradually disperse over cosmic time as the accelerating expansion of the universe, driven by dark energy, pulls distant regions apart faster than gravity can draw them together. The discovery of Laniakea revised understanding of the local group's cosmic address. Rather than being part of the Virgo Supercluster alone, the local group is part of this much larger structure, connected through gravitational flows to tens of thousands of other galaxies across hundreds of millions of light-years. This places the Milky Way in a broader cosmic context, part of one of the largest structures in the observable universe. Laniakea's structure reflects the cosmic web, the large-scale pattern of matter distribution shaped by dark matter and the expansion of the universe. The supercluster consists of filaments of galaxies separated by vast voids, a pattern that emerges naturally from the gravitational growth of structure from small initial density fluctuations. The filaments trace the densest regions of the dark matter distribution, where galaxies form and cluster. The study of Laniakea and similar structures provides insights into cosmology and the fundamental properties of the universe. The scale and mass of such structures constrain models of structure formation and the properties of dark matter. The bulk flows of galaxies within Laniakea test theories of gravity on the largest scales and provide information about the distribution of mass in the universe. Laniakea represents one of the largest coherent structures in the observable universe, but it is not unique. Similar superclusters exist throughout the cosmos, each containing tens of thousands of galaxies organized by gravity into vast networks of filaments and clusters. On the largest scales, the universe reveals a remarkable structure known as the cosmic web. This pattern consists of filaments of galaxies separated by vast voids, creating a network that resembles neural connections or a three-dimensional spider web. The cosmic web is the result of gravity acting on the initial density fluctuations present in the early universe, amplifying small overdensities into the massive structures observed today. The filaments of the cosmic web contain most of the universe's galaxies, strung along threads of dark matter that provide the gravitational framework for structure formation. These filaments can stretch for hundreds of millions of light years, connecting galaxy clusters and superclusters into a continuous network. The regions where filaments intersect host the largest galaxy clusters, massive concentrations containing thousands of galaxies. Between the filaments lie the cosmic voids, vast regions of space containing very few galaxies. These voids are not completely empty, but have significantly lower density than the cosmic average. The voids can span hundreds of millions of light years, representing the majority of the universe's volume. The galaxies that do exist in voids tend to be small, isolated systems, very different from the massive galaxies found in clusters. The cosmic web structure emerges naturally from the physics of structure formation. In the early universe, small quantum fluctuations during the inflationary epoch created density variations in the distribution of matter. As the universe expanded and cooled, gravity amplified these variations, pulling matter from underdense regions into overdense regions. Over billions of years, this process created the filamentary structure observed today. Dark matter plays a crucial role in forming the cosmic web. Because dark matter interacts only through gravity, it began collapsing into structures earlier than normal matter, which was initially too hot and too strongly coupled to radiation to collapse. The dark matter formed the gravitational scaffolding, and normal matter later fell into the dark matter potential wells, forming galaxies and stars. Observations of the cosmic web come from large galaxy surveys that map the three-dimensional distribution of galaxies across vast volumes of space. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the filamentary structure in exquisite detail. These maps show that the universe is remarkably homogeneous on the largest scales, with the cosmic web pattern repeating throughout the observable universe. The cosmic web also appears in the distribution of the intergalactic medium, the diffuse gas between galaxies. This gas, though extremely tenuous, traces the filaments of the cosmic web, with higher densities along filaments and lower densities in voids. The gas is heated to temperatures of hundreds of thousands to millions of degrees by gravitational collapse and feedback from galaxies, making it detectable through its absorption of light from distant quasars. The cosmic web is not static, but evolves over time. As the universe expands, the structure grows through continued gravitational collapse and the merging of smaller structures into larger ones. However, the accelerating expansion of the universe, driven by dark energy, limits the growth of structure. In the far future, the acceleration will prevent new structures from forming and will eventually pull existing structures apart. The cosmic web represents the largest scale on which structure exists in the universe. Beyond the scale of superclusters and the web's filaments, the universe becomes remarkably uniform, with no significant variations in density or structure. This transition to homogeneity occurs at scales of several hundred million light-years, beyond which the universe looks essentially the same in all directions. In the direction of the constellations Hydra and Centaurus, approximately 250 million light-years from the Milky Way, lies a mysterious mass concentration known as the Great Attractor. This structure exerts a powerful gravitational influence on galaxies throughout the local universe, including the Milky Way, pulling them toward it at hundreds of kilometers per second. The Great Attractor was discovered through observations of peculiar velocities, the motions of galaxies relative to the smooth expansion of the universe. Astronomers noticed that galaxies in a large region of space, including the local group, were moving toward a particular direction faster than the expansion of the universe alone would predict. This indicated a massive gravitational source pulling galaxies toward it. The Great Attractor is difficult to observe directly because it lies in the zone of avoidance, a region of the sky obscured by the Milky Way's disk. Dust and stars in our galaxy block visible light from objects beyond, making it challenging to identify and study the galaxies in that direction. However, observations in wavelengths that penetrate dust, such as infrared and X-rays, have revealed some of the structure. The Great Attractor region contains several massive galaxy clusters, including the Norma cluster and the Centaurus cluster. These clusters contain thousands of galaxies and have masses of tens of trillions of solar masses. The combined gravitational influence of these clusters and the dark matter halos surrounding them creates the attractive force that affects galaxy motions across hundreds of millions of light-years. However, the Great Attractor itself is not the ultimate source of the gravitational pull. Further observations revealed that the Great Attractor is itself moving toward an even more massive structure, the Shapley Supercluster, located approximately 650 million light-years from the Milky Way. The Shapley Supercluster is one of the most massive structures in the nearby universe, containing more than 8,000 galaxies with a total mass exceeding 10 to the 16th solar masses. The motion toward the Great Attractor and beyond reflects the hierarchical nature of structure in the universe. Galaxies are pulled toward groups, groups toward clusters, clusters toward superclusters, and superclusters toward even larger mass concentrations. This cascade of gravitational influence operates on scales up to hundreds of millions of light-years, creating large-scale flows of galaxies through space. The Great Attractor is part of the Laniakea supercluster, one of the major mass concentrations within that vast structure. The flow of galaxies toward the Great Attractor is one of the defining features of Laniakea, helping to delineate the supercluster's boundaries and structure. The local group's motion toward the Great Attractor is part of its overall trajectory through Laniakea. The existence of structures like the Great Attractor has implications for cosmology. The formation of such massive structures requires sufficient time for gravity to amplify density fluctuations, placing constraints on the age of the universe and the properties of dark matter. The large-scale flows of galaxies provide tests of gravitational theory on cosmic scales and offer insights into the distribution of matter in the universe. The Great Attractor represents a significant waypoint in mapping the cosmic address of the local group. It is a major landmark in the local universe, a gravitational beacon that influences the motions of galaxies across hundreds of millions of light-years, including the Milky Way and all its contents. At the ultimate limit of observation lies the cosmic horizon, the boundary beyond which light has not had time to reach Earth since the Big Bang. This horizon defines the observable universe, a sphere approximately 93 billion light-years in diameter centered on the observer. The size of the observable universe exceeds the distance light could travel in the age of the universe because space itself has been expanding during the light's journey. The cosmic horizon is not a physical boundary, but an observational limit. Beyond this horizon, the universe continues, possibly infinitely, but light from those regions has not yet reached Earth. As time passes, the observable universe grows as light from more distant regions arrives, though the accelerating expansion of the universe complicates this simple picture. The most distant objects observable are seen as they were in the early universe, billions of years ago. Looking outward in space is equivalent to looking backward in time, as the light from distant objects has taken billions of years to reach Earth. The most distant galaxies observed are seen as they appeared when the universe was only a few 100 million years old, small, irregular systems undergoing intense star formation. Beyond the most distant galaxies lies the cosmic microwave background, the thermal radiation left over from the Big Bang. This radiation was emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely through space. The cosmic microwave background appears as a nearly uniform glow at microwave wavelengths, with a temperature of 2.7 Kelvin coming from all directions in the sky. The cosmic microwave background marks the edge of the observable universe in terms of electromagnetic radiation. Before the emission of this radiation, the universe was opaque, filled with ionized plasma that scattered photons and prevented them from traveling freely. Observations cannot see beyond this surface of last scattering using light, though in principle, neutrinos and gravitational waves from earlier epochs could provide information about even earlier times. The structure of the observable universe on the largest scales appears remarkably uniform. After accounting for the cosmic web and the distribution of superclusters, the universe is homogeneous and isotropic, looking essentially the same in all directions. This uniformity supports the cosmological principle, the idea that the universe has no preferred location or direction, and that the laws of physics are the same everywhere. The cosmic horizon represents the ultimate boundary of the cosmic address. Every nested structure, from Earth to the local group to Laniakea to the cosmic web, exists within this vast sphere. The observable universe contains approximately 2 trillion galaxies, each with billions or trillions of stars, along with vast quantities of dark matter and dark energy that shape the universe's evolution. Beyond the cosmic horizon, the universe may extend infinitely, containing structures and galaxies forever beyond observation. The nature of the universe beyond the observable region is a matter of speculation and theory. It may be uniform, similar to the observable universe, or it may contain variations on scales larger than the observable universe itself. Some theories suggest the existence of a multiverse, with our observable universe being just one of many, each with potentially different physical properties. The cosmic horizon is gradually receding as the universe ages, but the accelerating expansion means that distant galaxies are moving away from Earth faster than light can travel. Eventually, galaxies beyond the local group will recede beyond the cosmic horizon, disappearing from view as the expansion carries them away faster than their light can reach Earth. In the far future, observers in the Milky Way will see a much emptier universe, with only the merged remnant of the local group visible against the cosmic microwave background. The journey outward has traced the nested structures of the cosmos, from the familiar surface of Earth to the ultimate boundary of observation. Each layer revealed a larger scale, a broader context, a more expansive perspective on the universe and our position within it. The progression moved through the technological shell of satellites, across the void to the moon, through the inner solar system's warmth, past the asteroid belt's boundary, beyond the Heliosphere's protective bubble, through the icy Oort Cloud, into interstellar space with its clouds and bubbles, along the Orion Arm's spiral structure, past the remnants of consumed galaxies, to the galactic core's massive black hole, through the halo's ancient stars, among the satellite galaxies, across intergalactic voids, within the local group's gravitational embrace, through the Virgo Supercluster's vast assembly, across Laniakea's immeasurable heaven, along the cosmic web's filaments, past the Great Attractor's pull, to the cosmic horizon's ultimate limit. This cosmic address places Earth and all its inhabitants in context. The planet orbits an ordinary star in the outer regions of an ordinary galaxy, part of a small galaxy group on the outskirts of a supercluster, flowing along filaments in the cosmic web toward distant mass concentrations, all contained within the observable universe's vast sphere. The scales involved are difficult to comprehend, each layer larger than the last by factors of thousands or millions. Yet the progression is orderly, each structure nested within the next, following patterns shaped by gravity, expansion, and the fundamental properties of space-time. The journey offers perspective without anxiety, wonder without overwhelm. The universe is vast, ancient, and largely indifferent to human concerns, and this realization can be deeply calming. The cosmic structures operate on timescales of millions and billions of years, their slow evolution continuing regardless of human activity or awareness. Understanding this cosmic address does not diminish human significance, but places it in context. Life on Earth, consciousness, civilization, all emerge from the same physical processes that shape galaxies and superclusters. The atoms in human bodies were forged in stellar cores. The energy that powers life comes from the sun. The very existence of stable planetary environments depends on the cosmic structures that organize matter on the largest scales. The map of the universe is a map of home, traced from the immediate to the ultimate, from the tangible to the theoretical. Each layer is real, each scale is measurable, each structure follows from the laws of physics operating across cosmic time. The journey outward is also a journey through understanding, revealing the architecture of existence from the ground beneath our feet to the edge of everything we can observe. For those seeking rest, this exploration offers a gentle intellectual journey without stress or urgency. The universe will continue its slow dance of expansion and evolution. The structures will persist. The patterns will remain. This knowledge can be soothing, a reminder of continuity and scale that transcends immediate concerns. The cosmic address is stable, the nested structures are enduring, and the journey through them can be revisited whenever calm reflection is desired.